Tonight, we're going to look at the universe through an instrument you've already heard described many times, and we're going to discover that your intuition about what it revealed is quietly, but fundamentally, incomplete. You've heard this before. You've seen the images. They look like sharper pictures of space, deeper views, more detail. It sounds simple. But here's what most people don't realize. The James Webb Space Telescope did not mainly show us new objects. It exposed a failure in how our minds handle scale distance, time, and accumulation once they cross a certain threshold. To feel that failure, we need one anchor, not a number. An experience. Imagine standing still while light moves away from you. Not racing, not blasting outward, just leaving. At the fastest speed anything can move. In a single second, it circles Earth more than 7 times. In a minute, it has passed the moon and kept going. In an hour, it has crossed distances that no spacecraft ever has. Now slow that down in your mind, not the speed of light, your experience of waiting. If you watched light travel for 1 year, doing nothing else, just waiting, it would still not have reached the nearest star. Not even close. You would still be watching emptiness. James Webb does not see faraway objects. It sees time that long ago stretched so far that it no longer behaves the way our intuition expects. It sees light that began its journey before Earth existed in its current form, before continents settled, before familiar skies ever formed. We tend to imagine the universe as a large place filled with objects. Webb forces a different frame. The universe is a layered archive of delayed information, and distance is not space, it is accumulated waiting. By the end of this documentary, we will understand why sharper images were never the real breakthrough. We will understand why galaxies appearing too early is not a surprise but a warning sign, and we will rebuild an intuition for scale that no longer collapses when distance turns into time, and time turns into structure. Now let's begin. Tonight, we're going to look at the universe through an instrument you've already heard described many times, and we're going to discover that your intuition about what it revealed is quietly, but fundamentally, incomplete. You've heard this before. You've seen the images. They look like sharper pictures of space, deeper views, more detail. It sounds simple. But here's what most people don't realize. The James Webb Space Telescope did not mainly show us new objects. It exposed a failure in how the human mind handles scale once distance turns into time and time turns into accumulation. To feel that failure, we need one anchor, not a number, but an experience. Imagine standing still while light moves away from you, not exploding outward, not accelerating, just leaving at the fastest speed anything can move. In a single second it circles Earth more than 7 times. In a minute it has passed the moon. In an hour it has crossed distances no human-made object ever will. Now hold that image and slow it down. Not the light itself, but your experience of waiting. If you watched light travel for 1 full year, doing nothing else, just waiting, it would still not have reached the nearest star. You would still be watching emptiness. This is already uncomfortable, because we are used to thinking of distance as something you cross, not something you endure. James Webb does not look far away in the way a camera looks far across a landscape. It looks backward in time. It collects light that has been travelling for billions of years, light that left its source before Earth had oxygen-rich air, before multicellular life stabilized, before continents arranged themselves into anything recognizable. What Webb receives is not an image of where something is. It is a record of when something was. This distinction sounds subtle, but it breaks intuition almost immediately. We are used to imagining the universe as a large container filled with objects at different positions. In that model, distance is just space between things. But when distance becomes large enough, space stops behaving like separation and starts behaving like delay. Every meter adds weighting. Every million kilometers adds more weighting. Every light year is not a place, but a duration. The universe that Webb observes is not laid out side by side. It is stacked in layers of time. At small scales, this difference does not matter. When you look across a room, the light travel time is so short that your brain treats it as 0. When you look at the moon, the delay is just over a second. You don't notice it. When you look at the sun, the light is about 8 minutes old, but your intuition still holds. The sun feels present. Nothing about daily life forces you to confront delay. Then the scales stretch. A star 10 light-years away is not 10 units of space. It is 10 years of waiting. The light reaching your eyes tonight left that star before today's children were born. At 100 light-years, you're seeing a century into the past. At 1,000, you're seeing civilizations rise and fall on Earth while the light was still on its way. Repeat this slowly. Distance is waiting. Distance is waiting. Distance is waiting. James Webb operates where this repetition finally overwhelms intuition. Its primary targets are not millions or thousands of light-years away, but billions. At that scale, you are no longer peering into a recent past. You are looking into epochs where the universe itself behaved differently, where matter was arranged differently, where the rules we casually apply had not yet settled into their familiar patterns. This is why the images were destabilizing, even if that wasn't obvious at first. When the first deep-field images were released, many people reacted to the clarity, the sharpness, the number of galaxies. But the real shock was not aesthetic, it was structural. Galaxies appeared mature, organized, heavy, far earlier than our intuition had prepared us for. They looked like things that should not yet exist. To understand why that matters, we need to slow down and rebuild what early means. The universe is about 13.8 billion years old. That sentence sounds like a fact, but it hides a trap. When we say early universe, most people imagine a time shortly after the beginning, vaguely compressed near 0. But 13.8 billion years is not a line with evenly spaced events in our minds. Our intuition compresses deep time until distinctions blur. James Webb does not look back a little. It looks back most of the way. Some of the light it detects left its source more than 13 billion years ago. That means it began travelling when the universe was less than 1 billion years old. At that stage, stars were just beginning to form in large numbers. Heavy elements were rare. Structures were supposed to be small, chaotic, and short-lived. That expectation came from models built carefully over decades, using observation, inference, and simulation. Those models were not guesses. They were constrained by physics we understand well. Gravity pulls matter together. Gas cools at certain rates. Radiation pushes back. Time limits how much structure can form. Here is where intuition fails again. We tend to imagine that given enough matter, things can assemble quickly. But assembly takes time, not just material. A galaxy is not a pile of stars dropped into place. It is the result of countless interactions, mergers, collapses, and feedback processes that unfold over hundreds of millions to billions of years. So when Webb shows galaxies that look massive and ordered very early on, the problem is not that they exist. The problem is how little time there seems to have been for them to become what they are. This does not mean the models were wrong in a simple way. It means scale has crossed another threshold where our assumptions about pacing no longer apply cleanly. We need to separate 3 things that are often blended together: what we observe, what we infer, and what we model. Observation is the light itself. Webb detects photons at specific wavelengths, stretched by the expansion of space. That stretching, called redshift, tells us how long the light has been travelling. This part is direct. It is measurement. Inference comes next. From the light spectrum and intensity, we infer properties: mass, age, star formation rate, chemical composition. These inferences rely on physics tested in closer, more recent environments. Modelling comes last. Models attempt to explain how such objects could have formed within the available time. given known physical laws. James Webb did not break observation. It strained inference and modelling. This is an important distinction, because it prevents a common mistake. Nothing about these results suggests the universe is mysterious in a mystical sense. There is no implication that the laws of physics stopped working. Instead, the telescope pushed us into a regime where small uncertainties previously tolerable accumulate into large mismatches. Accumulation is another intuition failure. At human scales, accumulation feels linear. 1 year plus another year feels like 2. At cosmic scales, accumulation compounds. Small differences in early conditions amplify over time. Slightly denser regions attract more matter faster. Slightly earlier star formation changes the surrounding environment, accelerating later growth. James Webb is sensitive to these early differences. It sees the compounded outcome, not the initial cause. Repeat this slowly. We do not see beginnings. We see consequences of beginnings. We do not see formation directly. We see what formation produced after waiting billions of years. This reframes the images entirely. Those distant galaxies are not snapshots taken long ago. They are messages that took most of the universe's lifetime to arrive. The universe is not showing us its youth directly. It is delivering delayed evidence of what its youth set in motion. At this point, something subtle happens to intuition. The universe stops feeling like a place and starts feeling like a process. Not a process unfolding in front of us, but one whose earlier phases are only accessible through long-delayed signals. James Webb is not powerful because it sees farther. It is powerful because it sees earlier consequences with higher fidelity, forcing us to confront how quickly structure may have emerged and how sensitive cosmic history is to its initial conditions. By now, we can restate what we understand. Distance is time. Time accumulates. Accumulation amplifies small differences. Webb observes the amplified outcomes, not the initial moments. The tension arises not from mystery, but from timing. This is the stable ground we stand on before going deeper. We have not overturned anything yet. We have only reached the point where familiar pacing fails, and where sharper vision reveals that our mental compression of early cosmic time was too aggressive. The universe did not suddenly become strange. Our intuition simply ran out of resolution. What happens next is almost always missed, because the human mind tries to stabilize too early. Once we accept that distance is time, it feels like the problem should be solved. We think we've adjusted. We imagine ourselves now looking backward along a timeline, seeing earlier stages stacked behind later ones. That feels manageable. It feels like a corrected picture. But that picture is still wrong. Because the universe is not static while light travels through it. While those photons were moving, space itself was changing, not shifting objects through space, but stretching the space between them. This is not motion in the everyday sense. Nothing is flying outward through a center. The distances themselves are increasing while the light is already on its way. This is where intuition collapses again, more quietly this time. When James Webb detects light from extremely distant galaxies, that light has not simply travelled a long distance. The distance has been growing the entire time. The photons were emitted when the universe was smaller, denser, and hotter. As they travelled, the space they moved through expanded, stretching their wavelengths. By the time they arrive, they are no longer the same light that was emitted. This stretching is redshift. At small scales, redshift feels like a technical detail. At large scales, it becomes the dominant effect. Imagine writing a letter and mailing it, but the paper itself stretches continuously while the letter is in transit. The words become longer, thinner, harder to recognize. You still receive information, but it arrives altered, distorted by the journey itself. That is what Webb is reading. This matters because the universe's expansion rate has not been constant. Early on, expansion behaved differently. Matter dominated. Gravity slowed the stretch. Later, dark energy became dominant and expansion accelerated. The light Webb sees pass through all of these regimes. It does not carry a single, clean timestamp. It carries an integrated history of expansion. So when we say a galaxy is 13 billion light-years away, that statement already hides layers of correction. The galaxy was closer when the light was emitted. The universe was younger. The expansion rate was different. Even the definition of distance depends on which moment in cosmic history you choose. Repeat this carefully. Distance is not one thing. Time is not one thing. Expansion reshapes both while the signal is still travelling. This is why the phrase early universe is more fragile than it sounds. When Webb shows galaxies that appear surprisingly large and structured, we instinctively ask how they could form so quickly. But quickly assumes a uniform clock. In reality, the early universe ran on a different tempo. Densities were higher, interactions were more frequent, cooling happened faster, gravity had more material to work with in smaller volumes. The same physical laws applied, but the conditions amplified their effects. This does not automatically resolve the tension, but it reframes it. What seemed like impossibly rapid growth may be less extreme once we stop projecting today's cosmic environment backward unchanged. Still, the discomfort remains. Because even after accounting for higher densities and faster interactions, some of the structures Webb observes push the upper edge of what models comfortably produce. Not wildly beyond, not catastrophically wrong, but close enough to force scrutiny. This is how real scientific stress appears, not as contradiction, but as pressure. To understand why this pressure matters, we need to revisit how our previous intuition was built. Before Webb, most deep observations relied on shorter wavelengths, especially visible light. That limited how far back we could see, because the earliest light is stretched into infrared by expansion. We were peering at the universe's past through a narrow window, missing much of the earlier structure simply because our instruments could not register it. Models were calibrated to that window. They worked well, they matched what we could see, they explained galaxy growth across billions of years. There was no crisis, there was no obvious gap. James Webb widened the window dramatically. It did not change the universe, it changed which parts of the universe could speak to us. Now we detect galaxies that were previously invisible, not because they were rare, but because their light had slipped outside our observational range. This introduces a subtle selection effect. The objects Webb reveals are not a random sample of all early galaxies. They are the brightest, most massive, most actively forming stars at that time. This is crucial. If you only hear the loudest voices in a crowd, you may conclude the crowd is louder than it truly is. Webb hears the loudest early galaxies. That does not mean all early galaxies were like that. Repeat this slowly. We are biased toward extremes. Extremes form faster. Extremes dominate early detection. Even with this bias accounted for, the observations remain informative. They tell us that extreme galaxy formation was already underway very early. That sets constraints. It tells us that the universe was capable of organizing matter efficiently under those conditions. The question becomes not how could any galaxies exist so early, but what fraction existed, and how representative are the ones we see. This shifts the tension from impossibility to calibration. At this point, another intuition often sneaks in unnoticed. We imagine galaxies forming smoothly, like buildings under construction, slowly rising floor by floor, but cosmic structure forms through violent processes, mergers, collapses, bursts of star formation followed by feedback that blows gas outward, shutting formation down temporarily. Early galaxies likely experienced extreme cycles, rapid growth, disruption, regrowth. Their apparent maturity may reflect brief luminous phases rather than long-term stability. Webb captures snapshots of these phases frozen by light travel time. We see moments, not lifetimes. This is another accumulation trap. We see a bright structure and assume persistence, but brightness often marks transience. The most active phases are short-lived, but they dominate what we observe. The deeper we go, the clearer the separation becomes between what the data directly says and what our intuition fills in. Directly, the data says there were luminous, massive, star-forming galaxies very early. Their light is redshifted into the infrared. Their spectra indicate significant stellar populations and heavy elements. What it does not say that all galaxies formed that way, that formation was uniform, or that the timeline was smooth. Our intuition wants a single story. The universe delivers a distribution. This is where modelling re-enters. Models are not pictures. They're computational experiments. We encode physical laws, initial conditions, and parameters, then let simulated universes evolve. We compare the outcomes statistically to observations. When tension appears, we adjust assumptions, not laws, unless forced. James Webb forces adjustments in areas that were previously weakly constrained star formation efficiency, feedback strength, early gas inflow rates, and the role of environment. None of these adjustments require new physics yet. They require better accounting. This is an important stabilizing point. The universe has not become unknowable. It has become more demanding. We are watching the scientific process in its normal state. Observation extends capability. Models strain. Assumptions are revisited. Understanding deepens. What Webb truly revealed here is not a contradiction, but the cost of underestimating scale. When time spans billions of years and conditions change continuously, intuition built on linear pacing fails repeatedly. By now, we can restate our updated frame. Light does not simply travel through space, it travels through an evolving universe. Early conditions accelerate processes. Observations are biased toward extremes. Apparent maturity does not imply long stability. Models bend before they break. This frame is stable, but it is not complete. Because we have not yet addressed the deepest distortion of all, the fact that the universe's expansion changes not only distance and light, but how volume, density, and probability behave over time. And once we confront that, even the idea of where something is will stop making sense in the way we expect. At this point, something subtle but decisive happens to our internal map of reality. Up to now, we have been stretching familiar ideas. Distance became time. Time became accumulated delay. Expansion altered the message while it travelled. These changes were uncomfortable, but they still allowed us to imagine a universe laid out along a timeline, with earlier and later states arranged in order. That picture is about to fail. Because expansion does not just change distances, it changes volume. And when volume changes, density changes. And when density changes, probability itself changes. This is where intuition trained on everyday experience finally collapses beyond repair. In daily life, volume is passive. A room stays the same size. A container holds what it holds. If you double the amount of material, density doubles. Nothing else shifts underneath you. Probability behaves quietly. The universe does not work this way. As space expands, the same amount of matter is spread over more volume. Density drops. But early on, volume was much smaller. Matter was packed tightly. Interactions were unavoidable. Collisions were frequent. Gravitational influence overlapped everywhere. Repeat this slowly. Early universe means small volume. Small volume means high density. High density means interaction is not optional. When James Webb looks into that era, it is not just seeing younger objects. It is seeing objects born in a fundamentally different statistical environment. In a sparse universe like today's, galaxies can evolve in relative isolation. They drift, interact occasionally, merge over long timescales. In the early universe, isolation barely existed. Everything was close enough to everything else to matter. This changes how we should think about likelihood. Events that seem rare today were common then. Processes that feel slow now were fast. Structures that appear improbable under current conditions were natural outcomes under early ones. This is not speculation. It follows directly from geometry and gravity. When volume increases, distances increase, and gravitational influence weakens with separation. But rewind the universe, and volume collapses inward. Everything crowds together. Gravity's reach overlaps. Small fluctuations matter enormously. This reframes the too early problem again. The question is no longer just how galaxies assembled quickly, but how difficult it would have been for them not to assemble under those conditions. Given enough density, collapse is not exceptional, it is inevitable. But inevitability brings another intuition failure. We tend to imagine inevitability as uniformity. If something is inevitable, we expect it to happen everywhere the same way. The early universe did not do that either. Density was not perfectly uniform. Tiny fluctuations existed from the beginning. Slightly denser regions pulled in more matter, became denser still, and accelerated ahead of their surroundings. Less dense regions fell behind. This process is called hierarchical structure formation, but the name hides its violence. It is not a smooth hierarchy, it is a runaway amplification. Repeat this carefully. Small differences grow. Growth creates larger differences. Larger differences accelerate growth. James Webb is sensitive to the winners of this process. The regions that started slightly ahead and then ran far ahead. That is what bright, massive early galaxies represent. They are not typical. They are extreme outcomes of an amplifying system. This does not make them misleading. It makes them informative. They tell us what the upper envelope of cosmic structure looked like under early conditions. They set constraints on how fast amplification can run before feedback slows it down. Feedback is another place where intuition misleads. In everyday systems, feedback is often stabilizing. Too much heat triggers cooling. Too much pressure causes release. We expect systems to self-regulate smoothly. In astrophysics, if feedback is violent and delayed, when stars form rapidly, they produce intense radiation, stellar winds, and eventually supernova explosions. These processes can blow gas out of galaxies, shutting down star formation. But this does not happen instantly. There is a lag. During that lag, growth can overshoot. Early galaxies likely experienced extreme overshoot, rapid gas inflow, explosive star formation, delayed feedback, sudden quenching, then recovery. Webb captures some of these galaxies mid-overshoot, at their brightest, most misleading moments. They look mature not because they are stable, but because they are temporarily extreme. This is another place where our everyday intuition about growth fails. We associate brightness and structure with age and stability. In the early universe, brightness often signals youth and instability. Hold that inversion carefully. Bright does not mean old. Organized does not mean settled. Now we need to confront a deeper distortion. When we imagine the early universe, we often picture fewer galaxies because less time has passed. Fewer things should exist. This assumes that creation is limited by time alone, but creation is also limited by opportunity. Opportunity was abundant early on. Gas was plentiful. Metals were scarce but not absent. Cooling pathways existed. Collisions were common. The universe had not yet diluted itself. As expansion progressed, opportunity decreased. Matter spread out. Gas fell into larger halos and became harder to access. Star formation slowed. Galaxies became more isolated. Growth stretched out. So paradoxically, the early universe was more productive per unit time than the later universe. Repeat this until it feels heavy. Early universe, faster productivity. Later universe, slower productivity. James Webb is sampling an era where productivity was high, where extreme outcomes were common, and where time moved differently in practical terms because everything interacted with everything else. This does not remove all tension, but it removes the illusion that early structure formation had to fight against scarcity. Scarcity came later. At this point, we can clarify another confusion that often arises. We sometimes imagine that seeing farther automatically means seeing simpler things. That is not guaranteed. Seeing farther means seeing under different conditions. Those conditions can produce complexity quickly if density and interaction rates allow it. The universe does not wait politely for our intuition to catch up. Now, consider what this means for the word scale itself. Scale is not just size or distance. Scale is the relationship between physical processes and the environment they operate in. The same laws produce different outcomes depending on density, volume, and time available. This is why models that worked well for later cosmic times can strain when applied directly to earlier ones without modification. The laws are the same, the regimes are not. James Webb has forced us into a regime change. This is not a failure of science. It is a reminder that models are local approximations. They are built where data exists. When data expands, models must stretch or be rebuilt. This brings us to a stable interim understanding. We now see that early galaxies are not anomalies floating in a void. They are extreme outcomes of dense, highly interactive conditions. Their apparent maturity reflects rapid, unstable growth rather than long-term equilibrium. Their brightness is a selection effect amplified by our instruments and by physics itself. Distance misled us, time misled us, volume misled us, probability misled us. One by one, these intuitions collapsed because they were built for a universe that no longer resembles the one Webb is showing us. But there is still one assumption left intact. Quietly shaping everything, we think we see the assumption that the universe's timeline is evenly meaningful everywhere, that earlier and later map cleanly onto development. That assumption is next. Because once we examine how cosmic time itself is defined, measured, and experienced across expansion, the idea of a single universal clock will quietly dissolve. The moment we try to place everything we've seen onto a single clock, the structure breaks. We speak casually about the age of the universe. We assign dates to events. We say one galaxy formed earlier than another, as if earlier were a simple position on a timeline shared by everything everywhere. This works just long enough to become dangerous. Because cosmic time is not experienced uniformly across space. It is not even defined uniformly once expansion becomes significant. To see why, we need to examine what a cosmic clock actually measures. On Earth, a clock measures cycles, atomic vibrations, rotations, oscillations. These are local processes occurring under local conditions. They assume stable space-time in the immediate environment. In cosmology, when we say the universe was 500 million years old, we are not pointing to a single clock that everything agreed on. We are defining a reference frame, a way of slicing the universe into moments based on its average expansion history. This is already an abstraction. Cosmic time is a bookkeeping tool. It works well statistically. It works well on large scales, but it hides variation. Different regions of the universe experience different local conditions, different densities, different gravitational potentials, different rates of structure formation, time, as experienced by physical processes, unfolded at different effective paces. This is not a philosophical statement. It is a physical one. Gravitational time dilation is small in everyday life, but it exists. Stronger gravity slows local clocks relative to weaker gravity. In the early universe, gravity was not evenly distributed. Dense regions ran on slightly different clocks than sparse ones. Over short intervals, this difference is negligible. Over hundreds of millions of years, it accumulates. Repeat this carefully. Small timing differences accumulate. Accumulation reshapes sequence. When we say two galaxies formed at the same time early on, we mean within a cosmological average. Locally, their internal histories could be offset in ways that matter for development. This undermines another intuition that early galaxies should all look similarly immature. They shouldn't. Even under identical physical laws, different environments produce different timelines. One region collapses early, another later. One experiences rapid gas inflow, another starves. One overshoots and quenches, another grows steadily. James Webb is not sampling a synchronized universe. It is sampling a desynchronized one. This becomes especially important when interpreting apparent ages. When Webb detects a galaxy with a large stellar mass and evolved stellar populations, we are tempted to translate that directly into a formation time. But stellar age estimates depend on assumptions about star formation history, metallicity, and feedback, all of which vary dramatically in early environments. What looks like a long, slow build-up under today's conditions could represent a short, intense burst under early ones. Time, here, is not linear effort, it is opportunity density. Early on, opportunity density was high, processes stacked quickly. A few 100 million years could accomplish what now takes billions. This does not violate cosmic time, it exploits it. So when we compress early history into the first billion years, we are compressing an era of extreme activity into a label that feels short, only because our intuition is anchored to today's pace. Repeat this until it settles. 1 billion years early is not equivalent to 1 billion years now. James Webb confronts us with this mismatch relentlessly. It shows outcomes that feel temporally misplaced because we are mapping them onto the wrong experiential scale. Now we need to address a related but deeper distortion, the assumption that cosmic history is a single narrative rather than a branching ensemble. In everyday history, we tell linear stories. One event leads to another. Alternatives are hypothetical. In cosmic history, alternatives all happened. Different regions followed different trajectories simultaneously. Some formed stars early and violently, some lagged, some merged quickly, some remained diffuse. All of these paths are real, and many coexist within the same cosmic time slice. James Webb captures a subset of these paths, not the average, not the median, a biased slice weighted toward luminosity and detectability. This means that the early universe, as seen by Webb, is not a representative snapshot. It is a highlight reel of extreme outcomes. That does not make it misleading. It makes it dangerous to overgeneralize. We must resist the urge to narrate a single story from these images. The universe did not follow one script. It explored many. This brings us to another intuition failure, the belief that clarity resolves uncertainty. Sharper images feel like they should settle debates. They do the opposite. As resolution increases, complexity increases, more parameters matter, more variation appears, simple narratives fracture. James Webb did not simplify the early universe. It revealed how many simplifying assumptions we'd been relying on without noticing. This is a healthy disruption. Now, consider how this affects the idea of formation time itself. Formation is not an event. It is a process with no sharp boundary. When does a galaxy form? When gas begins to collapse? When the first stars ignite? When a stable structure persists? When feedback regulates growth? Different definitions yield different answers. Early environments blur these distinctions further because processes overlap and recur. So when we say a galaxy already existed at a certain cosmic time, we are imposing a boundary where none naturally exists. James Webb shows us galaxies in the middle of becoming. We see them because they are bright at that moment, not because they have reached some final state. This reframes maturity again. Maturity is a moving target defined by our categories, not by the universe's behavior. At this point, a stable understanding begins to emerge. The early universe was not a quieter, simpler version of today. It was a denser, faster, more chaotic environment where multiple evolutionary paths unfolded simultaneously, unsynchronized and uneven. Time labels smooth this into a single curve. Webb peels that smoothing away. Distance misled us. Time misled us. Volume misled us. Probability misled us. Now, uniform chronology misleads us. Each correction narrows the gap between what we expect and what we observe. But there is still tension left, and it lives in a place we have not yet touched directly: the relationship between light, matter, and the limits of what observation itself can encode. Because even after correcting for expansion, density, bias, feedback, and time, we are still interpreting a universe using signals that have been filtered, stretched, and partially erased by the journey itself. And until we understand how much information is lost, not hidden, but fundamentally unavailable, we will continue to overinterpret what we see. That boundary is next. What we are finally forced to confront is not just how the universe behaves, but how little of that behavior can ever arrive intact. Up to now, we have treated light as a faithful messenger, delayed, stretched, biased toward extremes, yes, but still carrying the essential story of what happened. That assumption holds only until we ask a harder question: how much information survives the journey at all? Because light does not just travel through expanding space, it interacts, it scatters, it redshifts out of detectability, it blends signals together, and in some regimes, it never escapes in the first place. This is not a technical limitation of telescopes, it is a structural limitation of the universe. To see why, we need to strip away another intuition that seeing farther means seeing more completely. In everyday experience, distance mainly reduces clarity. Objects get smaller, blurrier, but their nature is still recoverable if you have enough resolution. Cosmology does not work that way. Past a certain scale, information is not merely degraded, it is destroyed. Consider what light must do to reach us from the early universe. It must escape dense regions filled with gas and dust. It must survive interactions with charged particles. It must avoid being absorbed and re-emitted at different energies. It must traverse epochs where the universe itself was opaque. For a significant stretch of early cosmic history, the universe was filled with neutral hydrogen that absorbed high-energy light efficiently. Photons produced during this time did not travel freely. They scattered, were reprocessed, or were trapped until conditions changed. This period is known as the Cosmic Dark Ages, but the name is misleading. It was not dark because nothing happened. It was dark because information could not travel. Repeat this carefully. Events occurred. Signals did not escape. James Webb does not see through this barrier. No instrument ever will, using light alone. The earliest eras of structure formation are partially sealed off, not by distance, but by physics. So when we look at the earliest galaxies Webb can detect, we are not seeing the beginning of galaxy formation. We are seeing the first moments when light from galaxies could travel freely. This distinction matters more than it sounds. It means the universe did not suddenly begin forming galaxies at the point we can observe. It means that before this point, galaxy formation was either hidden, muted, or expressed through signals we cannot easily detect today. What we call first galaxies are first visible galaxies. This is another intuition failure. Visibility feels like existence. In cosmology, visibility is conditional. Now consider what happens to light that does escape. As the universe expands, wavelengths stretch. This shifts information from higher energy bands into lower ones. Fine spectral features smear. Signals that were once distinct blend together. Separate populations become harder to disentangle. This is not just a loss of brightness. It is a loss of detail. James Webb is optimized to capture infrared light precisely because early universe signals have been stretched there. But even Webb cannot recover what was never encoded or what was erased during propagation. So when we infer properties like stellar age, mass, or metallicity from distant galaxies, we're doing so with incomplete data. We rely on models to fill gaps. Those models are grounded, but they are not direct reads of history. Repeat this slowly. Observation provides constraints, not full records. This brings us to a subtle but crucial separation, the difference between reconstructible history and actual history. Actual history includes every fluctuation, every collapse, every burst of star formation, whether or not it left a detectable signal. Reconstructible history includes only what left traces that survive to the present in measurable form. James Webb dramatically expands reconstructible history, but it does not close the gap. In fact, by pushing closer to the boundary where information becomes inaccessible, it makes that gap more visible. This is why claims about rewriting cosmic history must be handled carefully. Webb refines our reconstruction. It does not grant direct access to the full past. Now, another intuition must be dismantled, the idea that more data always resolves ambiguity. As we approach the information horizon, more data can increase uncertainty, not reduce it. Competing models can fit the same incomplete signals. Small differences in assumptions produce large differences in inferred history. This is not a failure of analysis. It is a reflection of fundamental limits. The universe does not guarantee that all of its past is observable. Some information is permanently beyond reach. This is where "we don't know" becomes a stable statement, not an admission of ignorance. We don't know exactly how the very first stars formed. We don't know how common earlier rapid galaxy assembly was beyond the brightest examples. We don't know how much structure existed before the universe became transparent. These are not mysteries waiting for better instruments alone. They are boundaries imposed by physics. James Webb brings us right up to those boundaries, and standing there changes how we interpret everything else. It forces us to downgrade certainty, to replace sharp timelines with probability ranges, to treat early observations as constraints on ensembles, not as definitive narratives. This also stabilizes the early attention. When Webb shows galaxies that seem too mature, part of that impression comes from interpreting limited signals as complete histories. Once we accept that we are seeing filtered, biased, incomplete records, the sense of impossibility softens. Not because the galaxies become less impressive, but because our claims become more careful. This is the quiet discipline of cosmology at extreme scale. Now, notice what has happened to our intuition since the beginning. We started with images that felt like photographs of distant places. We now understand them as partial messages from different regimes of physics, shaped by expansion, density, bias, timing, and information loss. We no longer ask, "What does this galaxy look like?" We ask, "What information about this galaxy could survive to reach us?" That is a more constrained but more accurate frame, and it prepares us for the next descent. Because light is not the only messenger the universe uses. There are other signals, relic radiation, background patterns, large-scale distributions that do not show objects at all, but encode statistical information about the universe as a whole. James Webb fits into this larger observational ecosystem. It does not stand alone. Its revelations must be integrated with signals that do not resemble images, but carry deeper constraints. To understand the true scale Webb revealed, we must now step away from objects entirely and confront patterns so large that individual galaxies become noise. Only then will we see why the universe's scale is not just vast in size, but vast in the way information itself is distributed. At the scale we are approaching now, objects stop being the primary carriers of meaning. Up close, structure is intuitive. We see stars, galaxies, clusters. We assign identities. We trace histories. But when the universe grows large enough, these discrete entities dissolve into statistics. Individual stories blur. Only patterns remain. This is not a limitation of perception. It is a consequence of scale. James Webb shows us extraordinary objects, but to understand what they imply, we must step back until even those objects lose their individuality. We must look at how matter is distributed overall, not where specific galaxies happen to be. This is where another intuition quietly fails. We are used to thinking that adding detail improves understanding. In cosmology, understanding often improves by discarding detail. Consider how weather works. You do not track every air molecule to understand a storm. You study pressure gradients, temperature fields, large-scale flows. The details average out. The pattern dominates. The universe behaves the same way. At the larger scales, matter arranges itself into a cosmic web of filaments, nodes, voids. Galaxies trace this structure, but they are not the structure itself. They are markers, like foam, outlining currents in water. James Webb detects galaxies embedded in this web, but it does not map the web directly. To see the web, we use statistical tools, surveys, and background signals that average over immense volumes. This shift from objects to distributions is essential. Because the two early galaxies Webb reveals are not isolated surprises. They occupy the densest regions of this web, where matter naturally concentrates first. Repeat this carefully. Dense regions collapse early. Early collapse produces early light. Early light is what Webb sees. This reframes the question yet again. The issue is not whether galaxies formed early everywhere. It is whether the underlying density field allowed some regions to form galaxies very early. And we already know the answer is yes. We know this because of another signal that does not look like an image at all: the cosmic microwave background. This faint radiation fills the universe uniformly. It is the cooled remnant of light released when the universe first became transparent, long before any galaxies existed. It carries a snapshot of the universe at about 380,000 years old. At first glance, it looks smooth, almost perfectly uniform. But buried in that uniformity are tiny fluctuations, temperature differences of about 1 part in 100,000. These fluctuations represent density differences, regions that were slightly denser than average and slightly less dense. Those differences are the seeds of everything that came later. Repeat this slowly. All structure grows from tiny initial differences. We have measured these fluctuations with extreme precision. We know their statistical properties. We know how large they were, how they were distributed, how they correlated across the sky. This information constrains how fast structure can form. It sets the initial conditions for all later evolution. James Webb's observations must be consistent with these constraints. And so far they are. The early massive galaxies Webb sees correspond to the high peaks of the initial density field rare, but expected outcomes of a distribution with known variance. This is why stepping back to patterns matters. It prevents us from mistaking rare events for impossible ones. If you only look at the tallest waves, the ocean seems violent. If you measure the entire surface statistically, the extremes fall into place. This does not mean the details are unimportant. It means they must be interpreted in context. Now consider another intuition failure, the idea that scale increases smoothly. We imagine zooming out gradually, passing through stars, galaxies, clusters, and then simply seeing more of the same. The universe does not scale like that. At some point, gravity stops dominating, expansion dominates, structures stop growing, voids grow faster than filaments, the web freezes in comoving coordinates. This transition happens quietly, but it matters. It means that there is a largest meaningful scale for structure formation. Beyond it, the universe does not organize into larger objects. It only expands. James Webb operates well below this scale. It sees structures while they are still forming, still interacting. But the patterns it reveals must align with the frozen large-scale distribution we observe today. So far, they do. This alignment is another stabilizing point. It tells us that despite surprises at the object level, the universe remains statistically consistent with its early blueprint. The blueprint did not specify individual galaxies, it specified probabilities. Now we need to confront one more intuition that collapses here, the belief that the universe has a center or privileged direction. When we look at images, we instinctively orient ourselves: foreground, background, near, far, central, peripheral. At cosmic scales, this framing fails completely. Every observer sees themselves at the center of their observable universe. The cosmic web surrounds every point. Expansion looks the same in every direction on average. James Webb's deepest images are not peering toward a special edge. They are sampling one direction through a statistically uniform universe. This uniformity is not perfect. There are anisotropies, but at large scales, no direction is special. This matters because it dissolves another common misconception that the early universe we see is a localized region that somehow developed differently from the rest. It didn't. It is representative of what existed everywhere, modulo statistical variation. This reinforces the pattern-based view. The universe's scale is not just large in extent, it is large in the sense that meaningful behavior emerges only statistically, not locally. James Webb revealed this indirectly by forcing us to integrate its object-level discoveries into a framework dominated by distributions and averages. We are no longer asking whether specific galaxies formed too early. We are asking whether the distribution of early luminous galaxies matches what a universe with known initial conditions should produce. That is a different question, and it has a stable answer. So far, the answer is yes with adjustments. Those adjustments refine how efficiently matter turns into stars, how feedback regulates growth, and how early environments differ from later ones. They do not overthrow the cosmic framework. By now, our intuition has shifted significantly. We no longer picture the universe as a static backdrop with objects sprinkled through it. We see it as an evolving statistical system, where rare extremes coexist with vast averages, and where individual surprises are expected within a constrained whole. This is the scale Webb has forced us to inhabit. But there is still one more escalation ahead. We have dealt with space, time, volume, probability, information loss, and large-scale patterns. The last remaining distortion lies in how we imagine the universe's edge, the limit of what exists versus the limit of what we can observe. Those two are not the same. And once we separate them, the true scale of the universe will finally come into focus. The confusion between what exists and what can be seen is one of the deepest and most persistent intuition failures we carry. We talk about the observable universe as if it were the universe. We show diagrams with circles, edges, horizons. We point to limits and imagine boundaries. This language is convenient, but it quietly embeds a false picture. Because the universe does not end where our vision ends. The observable universe is not a container, it is a record. It marks the furthest distance from which light has had time to reach us since the universe became transparent. That limit is not a wall in space, it is a limit in communication. Repeat this carefully. The edge of the observable universe is not where things stop, it is where messages stop arriving. James Webb operates entirely within this record. It does not push the boundary outward. It refines what we can read near it. This distinction matters because scale explodes once we stop equating observability with existence. The universe may be vastly larger than the portion we can observe. It may be finite or infinite. Current observations cannot decide. What we can say is that the observable region is not special, and there is no evidence that conditions abruptly change beyond it. So when Webb reveals galaxies near the observational limit, it is not showing us objects near the edge of existence. It is showing us objects whose signals barely had time to reach us. This reframes distance one last time. Distance is not how far something is. Distance is how long communication has been possible. The universe has only existed for a finite time. Light has only had that much time to travel. The observable universe is a sphere of delayed signals expanding as time passes, not a region carved out of space. This sphere grows not because the universe is expanding into something, but because time allows more signals to arrive. James Webb samples older layers of this signal sphere. It does not approach an edge, it approaches a communication horizon. Now consider what happens to intuition when we extend this idea. If the observable universe is just the part that can talk to us, then most of the universe, if it exists beyond, is silent not because it is empty, but because its signals have not arrived and may never arrive. This is not mystery, it is geometry plus time. This silence does not imply irrelevance, it implies inaccessibility. James Webb does not change this. No telescope ever will. The horizon is set by physics, not technology. So when we say Webb revealed the true scale of the universe, we must be precise. It revealed the true scale of what observation means, not the total size of existence. This is another stabilization point. We are not peering out toward an edge. We are reading deeper layers of a finite signal archive embedded in an effectively unbounded reality. Now, another intuition breaks. We tend to imagine that earlier signals are simpler, that closer to the beginning, the universe should be easier to understand, fewer objects, fewer interactions. But earlier signals are not simpler, they are more compressed. As we approach the communication horizon, information density increases. Many events overlap in fewer observable channels. Light carries more mixed histories. Separation becomes harder. So paradoxically, the deepest observations are the hardest to interpret, not the easiest. James Webb operates in this compressed regime. It is not opening a clear window. It is reading densely encoded messages. This explains why its results feel destabilizing. They do not slot cleanly into linear stories because they are not linear records. Now consider the emotional response people often have to these images, or vertigo, insignificance. These reactions are not wrong, but they are not useful for understanding. The correct response is recalibration. The universe is not overwhelming because it is large. It is overwhelming because it does not map onto human categories of place, time, and boundary. Once we accept that, the pressure eases. We no longer ask, how big is the universe really, as if there were a single number? We ask, what part of the universe can affect us, and how? The observable universe answers that everything beyond it is causally disconnected from our present, at least for now. This does not diminish its existence, it clarifies relevance. James Webb helps by sharpening the distinction between what we see and what exists. It forces us to stop imagining the cosmos as a globe with an edge and start imagining it as a dynamic causal network defined by signal travel and expansion. This is a hard transition, but a necessary one. Now, let's connect this back to the images themselves. When Webb shows thousands of galaxies in a tiny patch of sky, it is not showing a crowded region of space. It is showing a long column of time compressed into a small angle. Those galaxies are not near each other. They are separated by billions of years in light travel time. The image collapses depth into surface. This is another silent intuition failure. We look at a flat image and assume proximity. In reality, we are seeing layers upon layers stacked along our line of sight. So when we count galaxies in a deep field, we are not counting neighbours, we are counting epochs. Repeat this slowly. A deep image is a time stack, not a spatial cluster. James Webb's sensitivity allows us to stack further back than before, adding more layers. The image becomes denser, not because space is more crowded, but because time is deeper. This is why the images feel almost excessive. They contain more history than our intuition expects to see at once. Now consider the implication. If such a small patch of sky contains so many galaxies across so much time, then the total number of galaxies in the observable universe is enormous, not because space is packed, but because history is long. And beyond the observable universe, there may be vastly more history, more structure, more galaxies forever silent to us. This is not speculation layered on ignorance. It is a direct consequence of how expansion and signal travel work. We do not know the total size of the universe. We do know that the part we can observe is not the whole. James Webb makes this unavoidable by pushing us up against the communication horizon and showing us how much complexity already fits inside it. At this point, our intuition has been rebuilt almost completely. We no longer confuse distance with space. We no longer confuse early with simple. We no longer confuse visibility with existence. We no longer confuse images with neighborhoods. We see the universe as a layered, expanding, statistically structured system with hard observational boundaries. But one final correction remains. Even within the observable universe, not everything that exists can ever affect us. Expansion accelerates. Horizons change. Regions that are observable today may become unreachable tomorrow. Scale is not static, it evolves. And once we accept that, we can finally understand what kind of universe James Webb has revealed, not just large, but dynamically stratified by causality itself. That is the last descent. Once expansion begins to accelerate, scale stops being a backdrop and becomes an active filter. Up to this point, we have treated the observable universe as a growing archive, gradually admitting more signals as time passes. That picture is incomplete. Expansion does not just allow more light to arrive, it also prevents future light from ever reaching us. This is where another quiet intuition breaks. We assume that given enough time, everything observable in principle will eventually become observable in practice. The accelerating expansion of the universe makes that false. There are regions of the universe whose light will never reach us, no matter how long we wait, not because they are too far now, but because the space between us and them is growing faster than light can cross it. This does not violate relativity. Nothing is moving through space faster than light. Space itself is expanding. Distances increase faster than signals can close the gap. Repeat this carefully. There are events happening right now whose signals are already lost to us forever. This introduces a new kind of horizon, not a past boundary, but a future one. The observable universe is bounded in two directions. Backward, by how long the universe has existed. Forward, by how fast expansion accelerates. James Webb operates between these horizons. It looks backward toward the earliest accessible signals, but its discoveries also remind us that the universe's future visibility is shrinking. This adds another layer to scale. Scale is not just how big the universe is, scale is how much of it can ever matter to us causally. Now consider how this affects interpretation. When Webb reveals early galaxies near the edge of the observable universe, we are seeing objects that were once much closer, embedded in a region that, today, may already be receding from us faster than light due to expansion. We can see their past, but we will never see their future. This is another intuition failure. Seeing something does not imply an ongoing relationship. Those galaxies are not distant neighbours we could eventually reach. They're causally drifting away. The light we receive is a final message, not an invitation. Repeat this slowly. Observation does not imply accessibility. This reframes the idea of cosmic history again. The universe does not simply unfold and remain available. Parts of it fall permanently out of causal contact. Information becomes unreachable in both directions, hidden in the past by opacity, and sealed off in the future by expansion. James Webb sits in a narrowing window. It gives us the richest possible view of early structure just as the universe's future visibility declines. This is not poetic coincidence. It is a consequence of cosmic timing. Now, let's examine how this affects the meaning of now. In everyday life, now feels universal. In cosmology, there is no single global present that all regions share operationally. Different regions of the universe have different causal futures relative to us. Some will always remain connected, Some are already beyond reach, some are crossing that threshold now. The universe's scale is not just spatial, it is causal. James Webb does not show causality directly, but its discoveries force us to confront it. When we see early galaxies, we are seeing regions that once lay within a tighter causal network. Matter could influence matter over shorter distances. Expansion had not yet torn the network apart. As time progressed, that network stretched, thinned, and fractured. This changes how we should think about cosmic evolution. Evolution did not occur in a static arena. It occurred in a shrinking causal neighborhood. Early on, everything could interact. Later, interactions became localized. The universe gradually isolated itself. This is why early structure formation could be so rapid. Opportunity density was high, not just in matter, but in causality. Repeat this carefully. Early universe high causal connectivity, later universe causal isolation. James Webb reveals outcomes born in that highly connected phase. This perspective resolves another lingering confusion. We often imagine the universe as something that keeps getting larger and more complex over time. In some ways, the opposite is true. Large-scale connectivity peaked early. Complexity became increasingly compartmentalized. Galaxies, once forming in a tightly coupled network, became islands. Webb's images capture the universe before isolation fully set in. Now consider what this means for scale. The universe's true scale is not defined by how far it extends, but by how interaction changes across time. Scale is dynamic. It reshapes what can influence what. This is why simply quoting the size of the observable universe misses the point. The relevant scale is the causal scale, and that scale is evolving. James Webb pushes us to confront this because it forces us to interpret ancient signals arriving in a universe whose future is increasingly disconnected. This also stabilizes our expectations. We should not expect future telescopes to keep extending our reach indefinitely. There is a limit to how much of the universe can ever be observed, even in principle. James Webb is operating near the practical maximum for electromagnetic observation of early structure. This does not diminish its importance, it defines it. Now let's return briefly to the phrase that triggered much of the public reaction, the true scale of the universe. That scale is not just bigger than we thought. It is structured in a way that human intuition does not naturally handle. Parts of it are visible only in the past. Parts of it exist only in theory. Parts of it will never be accessible. The universe is not a map. It is a causal hierarchy unfolding over time. James Webb revealed this not by measuring farther, but by forcing us to integrate past visibility, present observation, and future inaccessibility into a single coherent frame. By now, our intuition has been rebuilt again. We understand that visibility is time-limited. Interaction is shrinking. Observation is asymmetric. History arrives, but futures recede. This is not unsettling once accepted, it is stabilizing. We no longer expect completeness, we expect boundaries. And this prepares us for the final phase of understanding. Because once causality itself becomes scale-dependent, the remaining question is not about size or distance, but about meaning within limits. Not philosophical meaning, but operational meaning, what knowledge is possible, what inference is justified, and what questions the universe itself will never answer, regardless of effort. James Webb has brought us to the edge of that clarity. Now, all that remains is to return to where we started, not to add new ideas, but to integrate everything into a stable picture of the reality we inhabit. At this stage, the universe no longer feels like something we are uncovering layer by layer. It feels like something we are negotiating terms with. Not because it resists understanding, but because it enforces limits so consistently that any remaining confusion now comes from us, not from it. This is where interpretation itself becomes the dominant challenge. James Webb did not just extend observation, It compressed interpretation. It forced many assumptions, once safely separated, to coexist in the same frame expansion, causality, bias, information loss, and statistical structure. Holding all of these at once is difficult, so the mind looks for shortcuts. One of the most persistent shortcuts is the belief that explanation must culminate in a picture. We want a final image, a diagram, a mental snapshot where everything fits. The universe does not offer one. At extreme scale, understanding is not pictorial, it is relational. We understand not what things look like, but how constraints interact. This is another intuition collapse. From childhood onward, comprehension is associated with visualization. If we can picture something clearly, we believe we understand it. When visualization fails, we feel lost. James Webb operates precisely where visualization stops being reliable. Its images feel concrete, but their meaning is abstract. They encode redshift, expansion history, selection effects, feedback cycles, and causal horizons all at once. No single image contains its own explanation, so interpretation becomes an act of restraint. We must continuously ask, what does this observation rule out, not what does it prove? This shift is subtle, but foundational. Early galaxies that appear massive do not prove that galaxy formation was universally fast. They rule out models where fast formation is impossible. They narrow the space of viable histories. This is how progress occurs at extreme scale. Not by confirming narratives, but by eliminating impossibilities. James Webb has eliminated several comforting simplifications. It has not replaced them with a single new story. It has replaced them with a constrained range of stories that must all fit the same statistical and physical boundaries. This is harder to hold in mind, but more stable. Now consider another intuition that dissolves here, the idea that knowledge accumulates smoothly. We often imagine science advancing like a steady zoom, each new instrument adding detail to an existing picture. At extreme scales, progress is discontinuous. New capability forces reorganization, not refinement. James Webb did not sharpen the Hubble picture. It broke the frame Hubble's picture lived in. Not because Hubble was wrong, but because it operated in a regime where certain simplifications were harmless. Those simplifications are no longer harmless. This is why early reactions framed Webb's results as shocking or revolutionary. They felt disruptive because they invalidated unspoken assumptions, not because they contradicted established physics. Once those assumptions are surfaced and removed, the shock fades. What remains is a more demanding form of understanding. Now let's address one final mental reflex, the urge to extrapolate. When we see early massive galaxies, the mind jumps forward. If galaxies were already so developed then, what does that imply about everything else? Does it mean stars formed earlier, planets earlier, life earlier? This reflex is natural. It is also unjustified. Each step in cosmic complexity depends on specific conditions. Fast galaxy assembly does not automatically imply fast planet formation, and planet formation does not imply life. James Webb reveals constraints on one layer of structure, not all layers. This is another place where scale must be respected. At large scales, gravity dominates. At smaller scales, chemistry matters. At smaller still, biology introduces new constraints. Extrapolating across these layers without careful modelling collapses understanding. So Webb's revelations must be kept in their proper domain. They inform cosmology. They constrain early structure formation. They refine the timing and efficiency of star formation. They do not rewrite everything downstream. This disciplined separation is part of cognitive stability. Now, notice something important. Despite all the revisions, limits, and recalibrations, nothing we have encountered required abandoning known physical laws. Gravity behaves as expected, expansion behaves as measured, radiation behaves as described. The universe did not surprise us by breaking rules. It surprised us by fully applying them in regimes our intuition was not prepared for. This is a critical point. When understanding fails at extreme scale, the failure is almost always in intuition, not in physics. James Webb exposed that failure gently, but relentlessly. Now let's consolidate what we have rebuilt so far. We understand that distance is accumulated delay. Expansion reshapes signals in transit. Early environments amplify growth. Observations are biased toward extremes. Time is not experienced uniformly. Information is filtered and partially erased. Large-scale patterns constrain local surprises. Visibility does not equal existence. Causality defines relevance. Future observation is limited. Interpretation must be probabilistic. Each of these corrections replaced a false simplicity with a constrained complexity. Together they form a stable frame. And now, for the first time, we can revisit the opening claim without distortion. James Webb did not reveal a universe that is merely larger than expected. It revealed a universe whose scale forces a different mode of understanding, one where images are inputs, not answers. This reframes the phrase "the true scale of the universe" one last time. The true scale is not measured in light years alone. It is measured in how many assumptions must be discarded to think coherently about what we observe. At human scales, few assumptions are needed. At cosmic scales, almost all of them fail. James Webb marks the point where failure becomes unavoidable. And once unavoidable, it becomes productive. Because from here on, questions become sharper. Not how big is the universe, but what can be known given these limits. Not why did this form so early, but what range of histories remain consistent with everything we observe. These are quieter questions, less dramatic, more precise. They are the questions that will guide cosmology for decades, not because they promise closure, but because they define the boundaries within which understanding can grow. At this point, we are no longer overwhelmed. We are oriented. We stand inside a universe that is vast, structured, constrained, and partially inaccessible, and we know exactly why. Only 3 sections remain, and they will not introduce new scale. They will return us to stability. By now, something important has shifted. We are no longer reacting to new images or new claims. We are operating inside a rebuilt frame. That frame is quiet. It does not demand resolution. It allows limits to exist without turning them into problems. This is the point where understanding stabilizes. And stabilization requires one last correction not about the universe, but about how we relate to it. Throughout this descent, we have repeatedly dismantled the idea that observation delivers direct access to reality. We replaced it with a layered process signals, filters, models, constraints. That process is now familiar. But there is one remaining intuition that still slips through unnoticed, the belief that the universe owes us coherence at human scales. We expect stories, we expect continuity, we expect explanations to feel complete. The universe does not operate at the scale of narrative. James Webb makes this unavoidable because it delivers information faster than narrative can absorb. It shows consequences without context, outcomes without beginnings, structure without clear ancestry. This feels disorienting only if we insist on narrative closure. But closure was never guaranteed. At extreme scale, coherence does not mean story, it means consistency. Consistency across physics, across statistics, across independent measurements. And this is where the calm returns. Because despite all the tension, all the recalibration, all the discarded intuition, the universe remains consistent with itself. The same expansion history that shapes the cosmic microwave background shapes the redshift of early galaxies. The same density fluctuations that seed large-scale structure constrain the earliest luminous objects. The same gravitational rules that govern galaxy clusters govern early collapse. Nothing we have seen violates this consistency. James Webb did not fracture the universe, it tightened it. This tightening changes the role of explanation. We are no longer trying to explain why the universe looks the way it does in a human sense. We are verifying that all observed features can coexist under the same physical rules and initial conditions. That is a quieter success than a dramatic breakthrough, but it is deeper. Now, consider how this reframes uncertainty. Earlier, uncertainty felt like something to be eliminated, a temporary gap awaiting better data. At this scale, uncertainty becomes structural. It defines the space of allowed histories. James Webb reduces uncertainty in some dimensions while revealing it more clearly in others. That is not a setback. It is refinement. For example, we now have tighter constraints on how massive early galaxies can be, how fast stars can form, how quickly feedback must act. At the same time, we acknowledge a wider range of plausible formation paths within those constraints. This is progress measured not by answers, but by narrowed possibility. Now notice what is absent. There is no moment where everything suddenly makes sense in a simple way. No final diagram where all arrows align cleanly. That expectation belonged to an earlier intuition. At extreme scale, understanding is not an endpoint, it is a stable operating region. We now operate inside a region where questions are well posed, even if answers remain probabilistic. This is the quiet achievement of James Webb. It did not deliver a new worldview, it delivered a usable one at scales where human intuition fails. Now let's bring this back to the opening idea. We began with the sense that the telescope showed us sharper images of distant objects. That intuition collapsed early. What Webb really revealed was the layered nature of cosmic reality time stacked into images, causality slicing what can be seen, expansion shaping what survives, statistics governing what dominates. At no point did the universe become stranger than physics allows. It became stranger than intuition allows. And intuition was rebuilt accordingly. This is why reactions framed around awe or insignificance miss the point. They are emotional shortcuts. The correct response is cognitive adaptation. We now know how to think about the universe without forcing it into human-scaled categories. We know where pictures help and where they mislead. We know which questions can be sharpened and which cannot be answered even in principle. This knowledge is not dramatic, it is durable. Now let's examine one final misconception that often appears at this stage. People sometimes assume that once a framework stabilizes, progress slows, that without dramatic surprises, discovery becomes incremental. At extreme scale, the opposite is true. Once the frame is stable, questions become precise. Precision accelerates progress. James Webb has created this condition. It has given cosmology a regime where early structure formation, expansion history, and statistical distribution intersect sharply enough that future observations can decisively favour some models over others. This is not an end, it is a narrowing. And narrowing is how understanding deepens. Now consider how this affects the future. Future telescopes will not replace Webb. They will complement it. They will probe different messengers, different wavelengths, different statistics, gravitational waves, large-scale surveys, high-resolution simulations. All of these will operate inside the same rebuilt intuition. James Webb did not just deliver data, it trained us to receive it without collapse. That is its lasting contribution. At this point, we are no longer descending, as we are leveling off. The remaining sections will not introduce new scale or new mechanisms. They will return us gently to the surface, carrying this rebuilt intuition with us. We will revisit the opening claim one final time, not to revise it, but to see it clearly. The universe is not larger than we imagined. It is structured in a way that required imagination to be replaced. And now, with that replacement complete, the universe feels stable again, not smaller. not tamed, but intelligible within its own limits. This is where understanding rests. What remains now is not discovery, but integration. Nothing new needs to be added, no additional scale needs to be introduced. The structure is already complete. What matters is how it holds together when we stop pushing and allow it to settle. This is the stage where intuition, once rebuilt, is tested for stability. We began with images that felt like windows. We now understand them as records filtered by time, expansion, causality, and probability. That understanding must persist without reinforcement. So let's restate the reality we're operating inside slowly, without escalation. The universe is not a place we look into. It is a process we intercept. Every observation is an intersection between what happened, what could travel, and what survived. James Webb sits precisely at that intersection. It does not show us the universe as it is now. It does not show us the universe as it was then. It shows us what remains communicable between those two states. This is not a limitation to be overcome. It is the definition of observation itself. Once this is accepted, confusion recedes. We stop asking why images do not line up with expectation. We ask which expectations were inappropriate to begin with. And most were. We expected linear timelines. The universe offers overlapping histories. We expected uniform pacing. The universe offers environment-dependent rates. We expected completeness. The universe offers bounded accessibility. We expected pictures. The universe offers constraints. None of this is hostile to understanding. It simply requires a different posture. Now consider how this posture changes interpretation of Webb's most publicized results. Early massive galaxies no longer feel like violations. They feel like confirmations that rare outcomes occur where probability allows them. High star formation rates no longer feel excessive. They feel consistent with high density, high connectivity regimes. Apparent maturity no longer feels premature. It feels like overshoot captured mid-phase. Nothing needs to be explained away. Everything needs to be contextualized. This is the calm that comes after recalibration. Now, another subtle shift occurs. We stop thinking of the universe as something that evolves toward us. We recognize that we are embedded within it, intercepting signals that happen to arrive here, now. Our position is not privileged in space, but it is specific in time. James Webb's revelations are only possible at this moment in cosmic history. Earlier, the signals had not arrived. Later, expansion will have carried them beyond reach. This is not coincidence, it is geometry. The universe allows certain questions to be asked only during certain eras. We happen to live during one of them. This does not make us central, it makes us timely. And timeliness is not meaning, it is opportunity. Now I consider how this affects the phrase true scale. Earlier, scale meant size, then it meant time, then causality, then information. Now it means opportunity. The scale of the universe is such that only a narrow slice of its total history is accessible to us in any useful way. James Webb occupies that slice optimally. This reframes the telescope's role again. It is not a tool for ultimate answers. It is a tool for maximum constraint. It pushes observation to the edge of what is possible with light, where additional reach would not add clarity, only ambiguity. That is not limitation, that is precision. At this point, the mind often seeks reassurance that something fundamental has been learned. Something has, not a fact, but a mode of thinking. We now know how to approach extreme scale without forcing it into human terms. We know how to separate what is seen from what is inferred. We know how to treat uncertainty as structure, not failure. We know how to stop asking the universe to behave narratively. This knowledge persists beyond any single telescope. Now let's examine one last internal check. Does anything we now understand conflict with earlier science? No. Hubble's discoveries still stand. Cosmic expansion still behaves as measured. The cosmic microwave background still encodes early conditions. Large-scale structure still follows gravitational growth. James Webb did not overturn these, it linked them more tightly. This continuity matters. Revolutions in science are often mischaracterized as breaks. At extreme scale, progress looks more like compression bringing previously separate ideas into unavoidable contact. Webb compressed early structure formation, expansion history, and observational limits into a single operational regime. That compression is uncomfortable at first, then it becomes normal. This is where we are now. The universe feels neither mysterious nor trivial. It feels constrained. Constrained in what can be observed, constrained in how structures can form, constrained in how narratives can be built. Constraints are not barriers, they are guides. They tell us where effort is productive and where it is not. James Webb has redrawn those boundaries clearly. Now they consider the future one last time without speculation. There will be refinements. Some early mass estimates will shift. Some star formation rates will be revised. Some models will be favoured over others. None of that will destabilize the frame. The frame is already stable because it is built on limits, not on surprise. This is the hallmark of mature understanding. At this point, we no longer feel the need to defend the universe against our expectations. We have replaced expectation with alignment. And alignment does not require closure. It requires coherence. The universe is coherent at extreme scale. James Webb helped us see that not by showing more, but by forcing us to see differently. Only one section remains. It will not introduce anything new. It will simply return us calmly to where we began with an image that no longer misleads us. Tonight, we began with something familiar. A telescope, images, distant galaxies rendered in extraordinary detail. At first glance, it looked like a straightforward extension of what we already knew: sharper vision, deeper reach, more of the same universe revealed. That intuition did not survive long. We learned that James Webb does not show distance as space, but distance as time accumulated. That what looks like a crowded field is a column of history compressed into a single view. That early does not mean simple, and bright does not mean mature. That visibility is conditional, causality is shrinking, and much of existence will never speak to us at all. None of this made the universe stranger. It made our previous intuitions inadequate. Now, as we return to the opening idea, nothing needs to be added, only reseen. When we look at a Webb image now, we no longer ask how far away those galaxies are in space. We understand how long their signals have been travelling and under what changing conditions. We understand that what we see is not a moment frozen in place, but a message that survived expansion, opacity, bias, and loss. We understand that each point of light is not an object alone, but a constraint on a much larger statistical system. The image has not changed. Our relationship to it has. This is the quiet result of rebuilding intuition instead of collecting facts. The universe no longer feels like a place with an edge. It feels like a causal structure with limits that move, boundaries that are real, and histories that overlap without aligning neatly. James Webb did not reveal the universe's size and a new unit. It revealed the cost of misunderstanding scale. We can now hold that cost without collapse. Distance no longer tricks us into imagining proximity. Time no longer tricks us into imagining simplicity. Early no longer tricks us into imagining immaturity. Visibility no longer tricks us into imagining completeness. And the unknown no longer tricks us into imagining mystery where there is only inaccessibility. This is stability. At the beginning, we said that most people misunderstand what James Webb revealed. That misunderstanding was never about data. It was about intuition. We expected pictures to behave like windows. We expected history to unfold like a timeline. We expected the universe to reward sharper vision with clarity. Instead, sharper vision revealed structure, limits, and constraints all at once. This is not disappointing. It is precise. Precision replaces drama. The universe does not need to overwhelm us to be large. It only needs to refuse our shortcuts. And now it has. When we step back into everyday scale, nothing breaks. The sky is still the sky. The stars still look the same. Our lives remain local, bounded, human. But beneath that familiarity, the rebuilt intuition holds. We know that every point of light carries delay. We know that every image hides compression. We know that every explanation is conditional on what could survive the journey to us. This knowledge does not intrude. It steadies. The universe is not asking to be admired. It is not asking to be feared. It is not asking to be given meaning. It is simply structured the way it is, and that structure is now clearer. James Webb's role in this was not to answer a question, but to force the right ones to exist. Questions that respect scale. Questions that accept limits. Questions that separate what is observed from what is inferred, and what is inferred from what is unknowable. That separation is the final calibration. So when we say that the James Webb Space Telescope revealed the true scale of the universe, we can finally say what that means without distortion. It revealed that scale is not just about how big things are. It is about how information moves, how causality narrows, how probability replaces narrative, how observation is bounded, and how understanding survives only when intuition is rebuilt to match reality, rather than forcing reality to match intuition. This is the universe we live in. We understand it better now, and the work continues.